So first, take a look of my updated figure here. The vector R, the moments arm is going towards the negative y direction, and the force F is going towards negative z direction. Now, and we discussed the difference between these two forces. For these two forces, for F1, because F1 is going in this direction, is going towards the z negative z direction. So the moment vector MC is going along the axis. It's parallel to the axis of the shaft. So it will lead to rotation. But for F2, the force is going along the axis, and the moment vector is perpendicular to the axis of the shaft. So MA of F2 will not lead to rotation. So therefore, we want to describe this mathematically. We want to use mathematics to make the difference between these two, or we distinguish these two. We distinguish these two cases. We want to distinguish these two cases, so we are using the dot product of the moments vector and the unit vector along the rotation of the shaft. Okay. We are carrying out the dot product between the moments vector and the unit vector along the axis, this rotation axis. And for this dot product, we will get a scalar here, for example, MC here, and therefore for this thing, because it's we are doing it with OC, so we are calling this moments of force about an axis OC. Moments of a force about an axis, about this axis OC. This is calculated by carrying out first a moment about a point on any point along OC, and then we carrying out the dot product with unit vector OC. Here, this one is R cross F. R cross F is the moments about a point, which is where is it? And here, moment about a point is here, right? R cross F. Remember, it's R cross F. And here, and now you may ask me, which point should we take as the reference? Which point should we take? Now, and it can be for this part, it can be any point along OC. So you can take the moment about O. You can take point C, and you can take point A as well. So this is any point along axis OC. We first take the moments about any point along the axis OC, and then we carry a dot product with the unit vector along the axis OC. So we cannot take B, okay? Or we cannot take B either. Any point along axis OC is okay. Let's do two examples. The first one is for F1. F1 is for F1. MOC is equal to for F1. Let's have a look. For F1, that this is F1. This is F1. First of all, we want to determine this one. We first determine the moments of F1 about 8 points on this line on axis OC. So the easiest thing to do is to take R1 and then F1, right? R1 cross F1, R1 cross F1, and this is what is this? This is moments about point. What? Which one? C, right? Because R1 goes from C to D. R1 goes from C to D. Therefore, for this R cross F, that what we calculate moments R cross the force, this one is about point C. And after we get or you can write NC here. And the next step is to carry out the dot product between this MC and the unit vector of OC here. And for F2, MOC is equal to. You can first write down, and I will give you time to write down. R2 cross F2, and then dot product of lambda OC. Let me make it a bit bigger. Is that okay? Now, can anybody remind me that is moments about which point is this moment with reference to? Moments about point, which one? We are doing R2 cross F2 here. So R2, F2 is here, and then we take R2 as the moment arm. So the point of reference is point A, okay? So moment about point A here. Anybody hasn't got this? The notes pages 33 to 44. Who hasn't got this? Now, for the next question, can we for F2? Of course, the most the direct choice, the most the most direct choice is to pick point A and then we do the moment arm as R2. But can we for this F2, can we take this point as reference and we take this as moment arm? R B with respect to C. Can we take this? The answer is yes or no. The answer is yes. And as long as this your point of reference is along axis OC, you can take it as the point of reference. Okay, so you can say this is R C R B with respect to C, and then cross F2, and then dot unit vector of OC. And this is the moment about point C. We can do this. We can do this. And we can do this as long as this one is moment about a point along axis OC. This is the key point. This is the key point. Then the point of reference R cross F should be along this along the axis. Actually, you can show mathematically that this one is equal to this one. You can do the mathematics. Okay. And let me write it down quickly. I can copy this for you. I'll give you the soft copy for this line. And so because RB with respect to C is equal to R2 plus RA with respect to C, right? And let's have a look. If we take this one as momentum R with B with respect to C is this one, it is equal to AC CA plus R2, right? It's okay. Now, if we have B with respect to C is equal to R plus RA with respect to C, and then R B with respect to C is cross F2 is equal to R2 cross F2 plus RA with respect to C cross F2. But since RA with respect to C is parallel to F2, so this one is equal to 0 because they are parallel to each other. Is that okay? take your time to write it down, and after you have written this down, please go to the previous page, the page before, and I will talk about the lower half of the page. Oh, by the way, and one last point. For if we do it in if we want to do this, if we want to work it out, doing the mathematics and to calculate the value, MOC is equal to lambda x, lambda y, lambda z, Rx, Ry, Rz, and Fx, Fy, Fz. And this one is, of course, a determinant, and it is on equation 3.44 in your textbook. So after you get the idea, if you want to work, if you are working on the homework, and this should be useful to you. Equation 3.44. Now, it's okay. And .44. So, and let's go to the. I will return to this page when you during the break. So, and in our determination of the moment above a line, we get we have cross products here, and we have dot products here. And it seems this is new, but yes, it is new, but it has a name by itself. It has a name. It is called mixed triple product of three vectors. It is like A dot B cross C. So, and this is called mixed triple products of three vectors, because there are three vectors in here. Now, so it has its meaning. It has its meaning, or it has its significance. Geometry is this one. So can anybody remind me? And for example, in this figure, we have three vectors A, B, and C. Can you tell me what can we get by doing this B cross C? Of course, you can say in Chinese or English. If we Have you learned this in high school? If we calculate B cross C, and what we will get? Yeah, is YT 几何上呢？功垂向量。就是说，另外一个是面积啊，就是说 ，so another one is so we will get the area of parallelogram。提到答案都对了，但是我想要那个几何上这样子啊，我要几何上那个意义。那当然你说弓垂也是，你说垂直那一个嘛哈，垂直那一个对哈。那 so we will get the area of the parallelogram because this line, because the length of this line is C sine theta, right? So the area is equal to BC sine theta. Just in case you forget, this is area. And if we determine if we get the mixed triple products A dot B cross C, we will get the volume of A, B, and C. We will get the volume of this zone defined by A, B, and C. Okay. But of course, we are using this to determine the moment of a force about a line. So this is 3 point. I think this is 3.34 again, and we will. I'll give you some homework on this week. So after we introduce these mixed triple products and the moments of a force above a line, we will do an example. I think this is also on the old version of the textbook, but not the newest one. Now, we have a 23 centimeter vertical rod CD. It's on page 28. Vertical rod CD. So, welded to the weld is this one. To the midpoint C of the 50 cm rod AB. Determine first the moment about AB of the 235 Newton force P, and the perpendicular distance between rod AB and the line of action of force P. Now, and now we are working on we work on the first part, and then we will work on the first part and then the second part. Now I will first do the wait a minute. The moments about AB, right? So we are going to determine the moments about AB. We do it in 2 steps. Of course, you can use one equation to do everything, because here we use one equation to do everything. Of course, you can do this, but the better way is to determine it in 2 steps. And this is the thing we want to get. AB or AC, this is up to you. And before we get this, we first determine the moment about points about any points on ACB, because the line AB is here. The line AB is here, so if we want to determine the moment about this line AB, we first determine the moment about any points along here. You can get moments about point A, moments about point C, or moments about point B, or any point in between. Now, we first get this one. We want to get this one, and of course we can choose. You can choose MA, MB, or MC. And then after you get this, and MAB is equal to this M dot lambda AB. It's okay. You can get anyone, and then you use this to carry out the dot product with unit vector of AB, and then you get MAB. So it depends on which one we want to use. Now I prefer using MB, but of course you can use any other points. Here I use MB, and then here we determine MAB is equal to MB dot lambda AB. Of course, you can take any other point as well. Now, and MB is equal to MB is equal to the force is acting on point. The force is acting on point D here. The force is acting on point D. So the moment arm is originally, you can say the moment arm is here. B. This one is the moment arm cross this one, right? If we take the moments along point about point B, is that okay? But we are doing one trick. And first of all, that we determine the line for line AB. We can determine the lambda AB. We first determine this one. We first determine this one. You can do it in any order as long as you write it down clearly. If you write every breakdown, it is okay. You do this first or you do that first, it is okay. Now, for lambda AB, it is here. And for MB, let me write it. Or I think I should write it down here. And if we do it like MB, it is, of course, from the figure, we will say it is equal to RD with respect to B cross P, right? Because the moment arm is here. It seems reasonable. But because the coordinates of D is quite it is somewhere in the 3D space. So it is the coordinates of D is here. So it is not easy to do the calculations. So in this sample problem, we do one trick. We use the principle of transmissibility. Originally, the force P is here, right? The force P is here. Now, for rigid body, we said that for rigid bodies that we can calculate the equivalence force by moving it to the front or moving it to the back. Okay, we can move it to the front or move it to the back. Now, if we move the force P to the front, and then something will become easier. If we move the force P here, if we move the force here, P here, and the moment arm will become this straight line. And the RG with respect to B is parallel to Z axis. Is that okay? Because the line of action of P is along DG, we can move the force to the front and go to here. We can move P here, and in this way, the moment arm is parallel to Z axis, so everything will become quite simple. So let me write it down. It's equal to RG with respect to B cross P. And remember, and as we have said, that P is let me write it here. So the line of action of P is along this line DG. It's along this line DG. So, and we first determine the unit vector along DG. It is on notes page 16, right? If you can't remember this, then please do more exercises. Therefore, P is equal to this one. G-MB is equal to, sorry. MB if is equal to RG with respect to B is equal to 57I plus 27J plus 9.5K Newton meter. And to give you an idea, G is equal to 7003 meter. I'm sorry, and I think I made one mistake. You can first write it down and I'll correct the mistake and afterwards. Now, and sorry that I made one mistake that, this one is not parallel to z-axis, but this one is not parallel to z-axis, but at least it is on the xz plane. So it is at least you are not dealing with 3 dimensions. Please correct this. Plane is right. If we go back to the calculations, and we will get an MAB, because MAB is equal to MAC, right? And it's equal to lambda AB dot MB, because we have got lambda AB here. We have got lambda AB here. We have MB here. So we can guess the moments about line AB as 24.84 Newton meter. You can check this at home. Is that okay? This is the answer. Let's have a quick look before the break.